Okay, so welcome everybody to this AJS. Today with us we have Anna Sanfilippo. She's a PhD student from University of Trento, and today she will talk about approximate deconvolution Leray reduced order model for Navier-Stokes equations. So Anna, the stage is yours.
Thank you. Thank you for the kind presentation and for inviting me here today. And as Anna said, today I will talk about approximate deconvolution Leray reduced order model for Navier-Stokes equations. That is a new regularized ROM that I developed with my PhD supervisor, Francesco Ballarin, from Università Cattolica del Sacro Cuore, and Ian Moore, a PhD student from Virginia Tech, and his PhD supervisor, Traian Iliescu, also from Virginia Tech. So I want to say also that this model was tested also for Burger's equation, but in this talk, I mainly focused on Navier-Stokes equations, since the test cases on 2D Navier-Stokes equations are the one I worked on. Instead, Ian worked on Burger's equations. So the goal, the aim of this talk is to discuss, describe, illustrate this new model that is flow control strategy for turbulent flows. That is flows characterized by large Reynolds numbers. And this model is characterized by high computational efficiency, especially in under-resolved or marginally resolved regime. That means when the dimension of the system correlated to the Navier-Stokes equations, in my case, is too small to properly represent the behavior of the flow we want to study. So to reach our aim, we used two ingredients mainly. The reduced order models that are the starting point of our research. They are Galerkin methods that are used to decrease the dimension of the system that are typically quite high in high fidelity approximation techniques. And the second ingredient is regularization techniques that are a practical way to handle flows with large Reynolds number, so turbulent flows, to handle poor starting data. And this is a key concept in our research, since we thought that one of the most challenging settings is when the starting data are not perfect or very smooth finite element solutions, but are poor finite element solutions, or even better, poor experimental data. And obviously, it's also a practical way to handle few basis functions, because the goal with Galerkin ROM is to use very few basis functions. So for all of them, I will discuss the methodology behind and also explain what practical means in the sentence above. And I will also show you a bunch of numerical test cases. And all this part is can be found in this article I published with Ian, Francesco, and Traian last year. That is a more computational paper in which we show and analyze ADL-ROM. Instead, now we are working on the numerical analysis of this model, and I will give you some hint on the theoretical part, but we don't have a paper yet for this, but we hope to submit it in the few next weeks. So first of all, I work on Navier-Stokes. So these are the incompressible Navier-Stokes equations, the first two lines, in which we have that U is the fluid velocity, P is the pressure, and nu is the viscosity. That is basically the inverse of the Reynolds number. And so in order to mimic turbulent flows, we have to choose a small viscosity or a large Reynolds number. And we equipped these equations with initial condition, U0, that is obviously a given data, and these boundary conditions. In particular, so we have non-homogeneous Dirichlet boundary conditions on the inlet, and also uin is obviously a given data. We have non-slip or homogeneous Dirichlet boundary conditions on the walls, and homogeneous Neumann boundary conditions on the outlet. So let's talk about our first ingredient, that is G-ROM. And as I said before, G-ROM is a quite famous and used technique to replace the high fidelity problem with one featuring a much lower numerical complexity. That, in other words, means we will use matrices and tensor with a small dimension compared to the one used in, for example, finite elements. And the reason why we wanted to use G-ROM is that high fidelity approximation techniques, one of the most famous, at least the one I used more in my experience, is finite element. And this type of techniques can become quite impractical when we want to solve the PDEs, in this case Navier-Stokes, multiple times. For example, if we want to study the problem for different time intervals or different parameters or different geometrical settings. And since run finite elements require, in our test cases, at least 12, 24 hours, do it a lot of times, it's obviously impractical from efficiency, running times point of view. So we started by using G-ROM. And G-ROM, in our case, is built upon data coming from a high fidelity discretization. So we solve once the finite element problem. And in this case, we chose to use Taylor-Hood finite element discretization in space. And Taylor-Hood is the classical couple of finite element used to solve Navier-Stokes, but there are other options that can be used as well. And as a time scheme or time discretization, we used implicit BDF2, even if we tried to use Crank-Nicholson BDF1. So it's not dependent only on this time discretization. And another thing that is very important is that we build our G-ROM upon data coming from a finite element solution. But our hope in the future is to use real experimental data, and in order to try more realistic problems, because obviously now we are using more toy problems or test cases more than real problems. And for doing, in order to try to mimic experimental data, we chose to use quite a coarse mesh, so H is quite big, and in this way the finite element solution is not perfect, is not smooth, and we can try our model on more complex initial data, let's say. Okay, but anyway, in any way you construct G-ROM, G-ROM always consists into different phases, the offline and the online phases. The first phase, the offline phase, has to be run only once, so in general is more time requiring, but it's not a problem since you run it and then store all the stuff you need in the online phase. That is the phase you have to run multiple times, or at least every time you want to study the problem you are interested in. So the offline phase, or also training stage, consists in building the reduced basis space and store the reduced basis functions and eigenvalues. To do this, we use the POD, or proper orthogonal decomposition technique, and basically we compress the temporary evolution of the finite element solution at given times. So we choose a time step, we compute the finite element solution at each time step, basically, and then we compress it. And this is equivalent to solve this minimization problem with this constraint that is basically saying that if you have two different basis functions or POD modes, you will have that the inner product is 0, otherwise it's 1. And from this minimization problem, we can also find the POD eigenvalues. So after solve this problem, we will have a set of basis functions or POD modes and the eigenvalues. And we denote the ROM space or reduced space as XR, and it is basically only the span of the first R POD modes of this as the solution of this problem. Obviously, R is set by the user. We chose the number of basis functions we want to use, but in order to have a meaningful G-ROM, of course, we have and we want to choose R very, very, very smaller than capital N, where capital N denotes the number of degrees of freedom in the full order model, that is to say, the dimension of the finite element problem. So after we concluded the offline phase, we will have available for the rest of the procedure all the basis functions we computed and the associated eigenvalues. So in the online phase or evaluation stage, we basically give meaning to the G in G-ROM, because it's here that we apply a Galerkin method, and it's quite the usual Galerkin method. So we assume the following expansion for the reduced velocity UR, basically setting it as a linear combination of the first R basis functions we chose and these time-dependent coefficients that are the unknowns now to properly reconstruct the reduced velocity. Obviously, all of the online stage is performed in the reduced space. Otherwise, it's meaningless. So to find these coefficients we want, we have to solve this problem that, first of all, can be fully discretized by using BDF2 or another time scheme for the time derivative. And it's basically the same as the formulation as the finite element problem associated with Navier-Stokes equations. So here we can rewrite it as a quadratically nonlinear dynamical system, in this case of small dimension R. So we will have the mass matrices, the mass matrix, the stiffness matrix, and the nonlinear tensor, that is basically a tensor, all of dimension R, and all these matrices and the tensor can be pre-assembled and stored once and for all at the end of the offline phase stage. So here, basically, you will compute the basis functions, you will save it along with the eigenvalues, and then you can also pre-assemble and store the matrices and the tensor. There is an exception, because if in the Navier-Stokes equations we didn't set the forcing term equal to 0, but the forcing term is different to 0, we will have a matrix also for the forcing term that can be pre-assembled and stored in the offline stage only if the forcing term is not time dependent. Otherwise, we have to compute the matrix for the forcing term in the online stage, and this requires a little bit of time more, but it's not a big problem because it's only one matrix, not all of the matrix. So another difference between this formulation and the finite element formulation is that we don't have the pressure anymore. And this is because for construction, all the POD modes are solenoidal and satisfy the appropriate boundary conditions we chose at the beginning. And so we can neglect the pressure. There are some cases in which you want to study also the reduced pressure. And so there is a formulation that takes into account also the pressure. but in our case, we weren't interested in studying the pressure at all, so we neglected it, and that's it. So we only have the velocity at the reduced level. Okay, so now this is G-ROM, and here we can compute the solution, the reduced solution. But as I said at the beginning, there are another ingredient that is regularized ROM. And why we want to add another ingredient to a method that I said is quite useful, is very popular, and is also quite relatable. The problem is that in the convection-dominated, so turbulent flows, under-resolved regime, so few basis functions, G-ROMs yields usually inaccurate results, in general in the form of numerical oscillations, spurious numerical oscillations. And this is obviously something that we don't want in general, having spurious numerical oscillations. And to prove it to you, I will show you Burger solutions, in this case not Navier-Stokes, because it's easier to visualize it with Burgers than with Navier-Stokes. And so here we have the finite element Burger solution with a quite small viscosity. And as I said before, also for Burgers, we don't have perfectly smooth finite element solution in order to try to mimic the experimental data. And so we have some oscillations here. But as we compute the G-ROM solution for very few basis functions, so only 10 basis functions, as you can see, the G-ROM solution is quite awkward everywhere. It's not only here the problem of the numerical oscillations, the spurious numerical oscillations are everywhere, and this is obviously a bad result in our opinion, at least. And so how to fix this numerical inaccuracy? There are a bunch of techniques and models to fix this type of inaccuracy, but one of the most popular and also practical are regularized ROMs that are based basically on using a ROM filter to smooth out all these spurious numerical oscillations. And it's practical in this sense. I mean, it's very easy to apply filters, to implement filters, and it's also not dependent on the problem, the domain, the characteristic your test case has. So in this sense, it's practical because, for example, other methods like closures depends more on the problem you are studying. So there is a lot of Reg-ROMs, and one that is very famous and also quite old is Leray ROM, called also L-ROM for short. And the idea behind this is very, very simple. We just choose a filter operator G, in this case, a ROM differential filter operator, that is the inverse of these, so of the identity minus delta squared the Laplacian. And ROM differential filter means that this operator has dimension R, as all the stuff in the G-ROM. So here we have a parameter delta that is called the radius of the filter, and delta has to be set at the beginning of the computation by the user. So in general, we chose delta that are related with the mesh size, but you have to be quite careful to choose an appropriate delta. Then we can write the filtered velocity as the operator G applied to the original velocity, in our case, to the reduced velocity. And this yields to this linear system of small dimension R. And again, this is the key. All these matrices are very small because, for example, if we take R equal 10, they are 10 times 10. And here we have, again, the mass matrix and the stiffness matrix that are be computed and stored during the offline stage are the same as G-ROM. And in this case, we have that since the problem we want to solve is to find U bar, we have that the vector of the POD time-dependent coefficients C is related to the reduced velocity, and this is the input variable. Instead, the output variable is the filtered velocity, and its coefficients are the C bar coefficients that are always time-dependent. So after that, we have to use this filtered velocity not in all the G-ROM formulation, but only in the nonlinear term in the Navier-Stokes equation, or better, in our case, in the G-ROM formulation of the Navier-Stokes equations. So instead of using U dot grad U, we will use U bar dot grad U. And so the proper L-ROM formulation is again a Galerkin method that means assuming these expansions, that the first one is the same of G-ROM, of course, it's the reduced velocity, and the second one is for the filtered velocity. And an important thing here is that we are using the same basis functions both for the reduced and the filtered velocities. So the basis functions are the same and are precomputed and stored during the offline phase, as I said before. And now we will have two sets of unknowns, the C and the C bar. And to find them, we will solve, first of all, basically the same formulation as G-ROM for Navier-Stokes equations, but with this U bar R in the nonlinear term. That is a sort of linearization of the nonlinear problem, since at each nonlinear step, what we do is compute U bar through this second system and using it in the nonlinear term. So it's true that we are adding another system to the problem, because obviously we don't have to solve anymore this only anymore, but we have to solve also these. But it's a linear system of small dimension R. It's not difficult to be solved by our solver, and so the running times and the speed up numbers are basically the same for G-ROM and L-ROM. So from the computational time, it's not heavier using L-ROM than G-ROM. So now, I said that G-ROM was good, but not good enough to properly describe the behavior of a turbulent flow. And then I introduced to you the L-ROM, saying the filter will fix the problem with the numerical inaccuracy. And so why do we think out another Reg-ROM? And the reason why is that it's true that L-ROM smooths out all the spurious numerical oscillations, but could be over-diffusive, since can smooth out also the physical oscillations and vortices you will find often in turbulent flows of Navier-Stokes equations. So our idea was to try to come back to something that is closer to the reduced velocity, so the original velocity, but less chaotic than the reduced velocity. So basically, we thought about approximate deconvolution operator that are called in general as the class of approximate deconvolution operators are called D. And what D is doing is that we took the filtered velocity, we applied D, and we come back to, in a certain sense, to the original reduced velocity. But in this way, we are also having a sort of, let's say, the smooth effect of L-ROM preserved, but in our experience only for the spurious numerical oscillations. So ADL-ROM should preserve the physical vortices and physical oscillations. At least that was our hope, and now we are happy with it. But at the beginning we didn't know, and so I will show you also the procedure to find that this is working during the results. So now, one question is why using approximate and not exact deconvolution? The reason why are two, and the first one is that in principle it would be useless, since G-1 will give in us the reduced velocity itself, and so it would coincide with the standard G-ROM with all the problem of standard G-ROM, so in numerical inaccuracy and blah blah blah. And the second reason is that in practice it's dangerous, since the exact deconvolution is not stable. So G-1 amplifies numerical errors, and this is something that everyone should avoid in this field. So we neglect the exact deconvolution and we go straight to approximate deconvolution. But as I said, for approximate deconvolution, we need approximate deconvolution operators. And we chose to use two different approximate deconvolution operators. The first one in the paper that is already available, and the second one for the numerical analysis part. But we can prove the numerical analysis part also for this operator or other operators, but the second one is more elegant in the proof. So the first one is also the simplest one and is called Navier-Stokes operator, and is defined as the mu, where mu is the characterizing parameter of Navier-Stokes, and is set by the user again at the beginning of the computation. And in this case, we will have that this problem solved in UAD is equivalent to the following linear system, always of small dimension R, where we have the stiffness and the mass matrices, all the parameters. And in this case, we will have that the input variable, so the known part, is the filtered velocity, and the unknown or the output variable is the approximate deconvolved velocity. Of course, in this case, we have the coefficients connected to the velocities, but it's the same. So instead, the second operator we studied is the Van Sitter operator, and is defined as the n, where n is the order of the Van Sitter operator. The order, since to solve this problem, we have to use Richardson iterations. So we don't have the same writing of the system before, but here we use Richardson iterations until the order we want to achieve, so capital N. Okay, so the ADL formulation in this case is always a Galerkin method, and so we assume the following expansions: the same as before for the reduced velocity, the same as before for the filtered velocity, and also in this case, for the approximate deconvolved velocity, we will use the same basis functions as before. So for all the velocities, we use the same basis functions. We don't have problem in storage, in efficiency. It's pretty simple as it is. And in this case, obviously, we will have an additional unknown, that is the coefficients that are the coefficients for the approximate deconvolved velocity. So to find all these unknowns, we have to solve, first of all, the classical Navier-Stokes problem formulation, in which we have in the nonlinear term the approximate deconvolved velocity. So instead of the classical reduced velocity or the filtered velocity as in L-ROM, we will use the approximate deconvolved velocity, UAD. And to in this case is written for Navier-Stokes, but for Van Sitter, it only changes the last row, in which we will use Richardson instead of this linear system, but it's basically the same. So at each nonlinear step, in order to find the unknown UAD and to can use it in the nonlinear term, we have to solve, first of all, the linear system for to find U bar, and then the linear system or capital N Richardson iterations to find UAD. So also in this case, we are adding for example, in this case, another linear system of small dimension R. But again, as for L-ROM, this is not a problem from the point of view of computational efficiency, since it's linear, it's only of dimension R, and it's quite straightforward to have the solution. So we studied that both the running times and the speed up numbers, that are basically the number you use to understand how is quicker the G-ROM, or in general the ROM solution, in comparison with the finite element solution, are very similar for G-ROM, ADL-ROM, and L-ROM. So now some results. First of all, we have what we called preliminary results, that are the results that we used to confirm to ourselves that this new model could work. So we didn't solve properly L-ROM and ADL-ROM in this context. We just use G-ROM solution, and then in post-processing we applied to it a filter and an approximate deconvolution operator, specifically the Lavrentiev approximate deconvolution operator. So for this test, we used the 2D flow past cylinder domain. We set all the stuff we need, so the time interval, the time step. We collect 400 snapshots over the whole time interval, and the snapshots are the finite element solution at the given times. And then we chose this viscosity that is quite small, this filter, and for the Lavrentiev regularization parameter, so mu, we chose 3 values. The first one is 0, that is basically exact deconvolution, so no more approximate, but only to confirm the theoretical expectation that the exact deconvolution is a bad idea. Then we tried mu equal to 0.03 and 0.3. Moreover, we use for all the simulations, not only in preliminary results, but in general, all the results are made from by using the UrbanXX software. That is a software that my PhD supervisor started to develop in late December 2021, and that I'm helping to enrich with some tutorials. So the preliminary results, here we have the normalized singular values from the POD procedure that basically tell us how much difficulties we can find by using few basis functions, since basically this means how much retained energy is having the problem with, I don't know, 10 basis functions here, for example. And so the decrease is quite slow, and this means that the problem is quite difficult. And here we have some solutions. So in this case, we used all the basis functions we had, so 50, and we studied the solution at the final time. So the top solution is the G-ROM solution, so the reduced solution itself. And we have some problems around the cylinder and after the cylinder is too dark. That means there are something happening that shouldn't. The second one is the filtered reduced solution. And as you can see, basically it smooths out everything. All we have also that is physical, for example, also in the physical solution, here we want some waves. Here is basically flat, and after the cylinder there isn't nothing, and so it's not good. And the third one is the approximate deconvolved filter velocity. So in this case, we don't have the same numerical instability that we had in the reduced basis solution, but we have more physical waves and physical behavior than in L-ROM. So this confirmed at the beginning our idea to proceed with the study of ADL-ROM. And here we have basically the same thing. The only difference is that we take the reduced solution, we filtered it, we add manually some noise to the filtered solution in order to see how the approximate deconvolution operator behaves when we have more noise. And the first approximate deconvolved solution is with mu equals 0. So this is exact deconvolution, and this is why we don't use exact deconvolution, since it amplifies too much the noises. And here we have the two solutions with different mu's. We have mu equal 0.03 as fifth, and as sixth we have mu equal 0.3. And in this case, we have that the better result is the one with mu equal 0.3. But in general, if the noises are not manually added, smaller values of mu working better. So now the real and proper results. So here we solved properly L-ROM and ADL-ROM. In this case, we used backward facing step domain with a smaller nu, that means a larger Reynolds number. And in this case, we wanted to make all the setting as challenging as possible for ADL-ROM. So we chose a more challenging domain, a more challenging viscosity, and moreover, we also chose to use very few POD modes or basis functions, only 10. And this is challenging, but also very attractive because it results in large speed up. So it's a very, very, very efficient and quick ROM solutions in general. Moreover, we chose a very, very large delta, 0.6, that is basically the average dimension of the mesh size. And this obviously means over-diffusive, very over-diffusive L-ROM. And this is a challenge for AD, since it should compensate this over-diffusive behavior. And then after some tuning, we chose to use mu equal 0.06. And here again, we have the normalized singular values from the POD procedure until 60 basis functions. And here the decrease seems more stiff, but it's not in reality. If you can remember the scale, the other one was the end of the other one was lower. So again, a very challenging problem, and especially for 10 basis functions is not a good retained energy. So here we have the solutions at the final time for all the parameters I set in the beginning of this part of the presentation. So here we have the finite element solution. It's not smooth, it's not perfect. As I said before, we didn't want very smooth finite element solutions. The second one is the G-ROM solution, and something is happening here, and there are some parts that in the finite element solution aren't present, like here. And then we have the L-ROM solution that is basically smoothing out everything. And so again, it's not good. We want the physical vortices. And then the ADL solution that at the first glance is the better one, the best one between these three, since it seems to preserve better the physical vortices, not perfect, but better. And also the pointwise error is confirming it. So these are the pointwise errors between the finite element solution and the G-ROM solution, the finite element solution and the L-ROM solution, and the finite element solution and the ADL solution. So also for the pointwise error point of view, we have that in general, the lower errors are from ADL. And this is confirmed also by the kinetic energy. We have in black the finite element kinetic energy, in red the G-ROM kinetic energy that is higher than the black one, and this means numerical spurious numerical oscillations. And then in green the L-ROM kinetic energy that is lower than the black line, and this means over diffusive behavior. And in blue the ADL-ROM kinetic energy, that is the one closest to the black line. It's not perfect, but it's closest, and this is a quite good results starting from so poor data, so from a finite element solution that is not smooth at all. And also the relative and absolute too, because are very similar graphs. L2 errors confirms our expectations, since ADL-ROM has the smallest error at the final time, but also on average on all the time interval. And so all these and more details and more graphs and more comments are about this part are present in this article. But now we are trying to prove something about the theoretical part. So first of all, we wanted to extend the estimates existing for the approximate deconvolution operators at the FOM level to ROM level, and the FOM level ones are being proved by Layton and Reblotz in this article of 2012. And moreover, we want obviously to find the ADL-ROM error estimates for Navier-Stokes equations. And we did it in this theorem, that is ADL-ROM error bound, in which we have that the error bound at the final time is that the error at the final time is bounded by this constant in which we have the parameter of the AD operator. So in this case, we used Van Sittert, so no mu, but the order, capital N, and we have it in the constant. And this operator that bounds the error, in which we have 4 control parameters: delta, the time step, the mesh size, and basically this can be reduced to the truncation error. So since this operator is quite ugly to be explained and to be also read, we will talk about the parameter scalings. That is basically the same as the operator F, but in a cuter and more readable way. So as I said, we have 4 control parameters that are H, delta T, delta, and R, the number of basis functions. But we didn't study H, we kept H fixed, so we only have 3 parameter scalings that are basically saying that the L2 error at the final time is linear in time and in the truncation error. That is this sum and means basically what we are neglecting by using only R and not capital R basis functions. And quadratic in delta, so in the filter, in the radius of the filter. And for doing the numerical test in this case, we use this problem in which we have the unit square as domain, this exact solution, because obviously to prove the numerical, the theoretical rates, we want a numerical, an exact solution. And we use the exact solution as snapshots in this case, not the finite element solution. And we use the POD, we compress them, we take 100 basis functions, and we calculate these rates of convergence for now only with respect to the filter radius and the truncation error. We are finishing now the last test for the time step. So with respect to delta, we fully numerically recovered the theoretical rate of convergence, since we have 1.96 and the theoretical one was 2, so very good. With respect to the truncation error, here we have a very better result than the theoretical expectations, since we have 1.71 and the theoretical expectation was 1. And so we recovered obviously the theoretical expectation, but it's strange to have such a better result. And our interpretation is that the problem is this dot in the top right corner that corresponds to the 10 modes, in which we have a very large error, since the coefficients in the arctan -500, it creates very steep waves. And so it's a very difficult problem to be described, fully described by only 10 basis functions due to these very stiff waves. So it's explicable by this behavior, this very, very good rate we reached. So for now, we can say that from the computational and empirical point of view, ADL-ROM is performing very well, produce very good results for Navier-Stokes equations, also for Burger's equation, but I didn't show you this. And from the theoretical point of view, the proofs are done, and we could prove that it's a good and stable method, but we have to publish soon the article, since we have to finish the numerical results for the theoretical paper. And in the end, I want to thank the ARIA project to found this research. Thank you.
Okay, thank you, Anna, for the nice talk. So it's time for questions. Okay, so are there any questions from people here in presence in the room? Not for now. From people online? If yes, just unmute yourself. It seems not for now. Okay, I can start breaking the ice. Can you come back to the test case of the flow past the cylinder?
Yes.
Like a curiosity.
Here.
Okay, okay, so the Reynolds number here was 100, right?
Yes.
Okay, 100. So did you try with the higher Reynolds number for this test case?
No, because at least we tried slightly higher Reynolds number, but the problem was that we used very coarse meshes, and so by raising too much the Reynolds number produces that the finite element problem doesn't converge. And so if the finite element solution is not converging, we can't go on to G-ROM, or better, we can, but it's quite useless. We can construct a good basis functions.
Yeah, like using a finer mesh then maybe will lead to like more computational costs also.
Yes.
Okay. And actually another curiosity, it's about the deconvolution, approximate deconvolution Leray-ROM. So if I remember correctly, it's slide 12, so the one before this one. Okay, yes, this formulation here. So basically, in L-ROM and ADL-ROM, you have this velocity UAD in the nonlinear term, but only in one of the two velocity terms. And I was wondering, I don't know if you know, it's something that it was already like proven, or if someone already tried. What happens if this approximate deconvolution is also in the other velocity, in the nonlinear term?
Okay. From a practical point of view, basically the nonlinear term, if is replaced with both the velocities reduced or approximate deconvolved, it's the same. It's not anymore a proper unknown. So you are not more solving the problem for the velocities itself, because at each nonlinear step you can properly compute these. So if you have these here and also here, these in a certain sense is becoming a forcing term, not more a proper part of the problem for you, because we are always solving the problem for UR. UR is what we want to have in the end. And so it's basically replacing the problem in U and mixing it with a problem in UR or U bar or UAD.
Okay. Okay, another life curiosity that I had is how much did you struggle to find the optimal values for delta and mu?
A lot. Like months.
I imagined, okay. And because, I don't know, maybe for delta, you use the, like the mesh size of someone close to the mesh size. But for mu, there is like literal choice or not?
For mu, no, there isn't any kind of constraint or advice to choose it. And so we just tune and tune and tune by changing mu and trying stuff. For capital N, so in Van Sitter, there are some studies on how to choose capital N at POM level, but we can reproduce it at ROM level, obviously. So for Van Sitter, is easier to choose the order of the operator than in Lavientiev to choose mu. That is basically on luck by trying.
Okay. And another curiosity that came now in my mind was at the POM level, you have Navier-Stokes. You have, sorry, only the formulation without any regularization, right?
It depends. So in this case, so the 2D flow past the cylinder and in the unit square, let's say, we don't have any type of regularization. In this case, so the backward facing step, we use EFR at the finite element level.
Okay. That was just a curiosity because sometimes, as you said, also the finite element is like poor at the font level. So yeah. Okay. So are there any other curiosities? Maybe online? Okay, I don't see any other curiosities, so I think we can stop. Let's thank again our speaker.
Thank you.
Okay, and see you at the next AJS.